Okay, last time we finished up chapter 2, and again, as we talked about, because of the holiday, chapter 3 was posted. Not a really long chapter. Hopefully, you watched it because it does relate to sort of the experiments we're doing today. So we're going to go to chapter 10 next, which should be, I believe, the last chapter on the first exam that we're going to kind of cover. So we're going to go ahead a little here, and we're going to talk about energy in this chapter. And let's talk a little bit about when we talk about energy, it is part of chemistry, which is sometimes referred to as thermodynamics. And thermodynamics a lot of times deals with the energy associated with reactions. Later on, when you take perhaps 1B, you'll talk more about thermodynamics, and it has to do with whether or not, for example, a reaction will take place under certain conditions. But usually, when we talk about energy and sort of thermodynamics in general, there's two parts of sort of the situation that we look at, and one is the system. And the system's really any part of the sort of universe that you're interested in. So, for example, when you're doing an experiment, maybe in a test tube or something like that, your system is the test tube. Then everything outside of like your system or your test tube, for example, is considered the surroundings. And what we're going to sort of talk about is this idea of when we talk about energy, it flows, kind of from, in certain cases, the system to the surrounding. It may kind of release some energy to the surrounding. So, for example, if you did some type of reaction like light your Bunsen burner, which is a chemical reaction, you will see fire, which is obviously giving off heat to the surrounding air, right? And it's picking up that energy. There are certain processes, as we'll talk about, where the surrounding itself will actually kind of send energy into the system. And, just an example of that is, for example, if you take ice out and just put it in room temperature, the ice cube is going to pick up heat and energy from the surrounding air and will start to melt, obviously. So the flow of energy can kind of go both ways to go from the system to the surrounding, surrounding to the system. One of the things we sort of think about when we're talking about energy and sort of context here of chemistry for sure is the idea that there's sort of this kind of perfect exchange of energy, which means if somebody loses a certain amount of energy, somebody else must gain the exact same amount, or that energy must end up somewhere, dispersed somewhere. So we never kind of lose energy or gain energy, which, as we'll see, is the law of conservation of energy. When we talk about the system, there's three types of system. There's an open system, and in an open system, you pretty much can exchange mass and also energy with the surroundings. So, for example, if you just think like an open beaker, you could go in there and take stuff out of the beaker, right? What's actually in it. It also can pick up some energy and stuff from the surroundings or release some energy from the surroundings. A closed system, on the other hand, we have transfer of energy but not mass. So, for example, if you're working with like a test tube that had a stopper on it, right? You couldn't get in there because it's covered. You can't exchange any of the mass that's inside, but you can still do the energy. And an isolated system is one where there's really no exchange of either mass nor energy. It is basically self-contained within that surroundings, basically. And here's sort of an example of that. Here again, we could take stuff in and out, remove mass, still have a heat exchange here by sort of stopping the exit of anything. And that can be either man-made exit, if you will, like you going in and taking it out, and also just natural. For example, if you had a liquid, right, it would start to evaporate, right, and you lose some through evaporation. So again, by putting that cover on it, it prevents any, even if you don't do it, anything to be able to get out of that. And that's a closed system. We still have that exchange of heat. And again, in an isolated system, we're really not going to have any exchange sort of happening. So when we talk about energy, energy is the capacity to do work, and energy is basically work done force times distance. There are different types of energy that we come across. There's chemical energy. For example, there's energy sort of stored within bonds. So when we have a chemical reaction that takes place, there's actually a sort of difference in energy that can occur between where the starting material starts and the ending material ends, and all the bonds that are either broken or made in that process. There is an energy sort of calculation that you can do to see what the overall change in energy occurs. For example, we talked a little bit about energy earlier, and we'll see it again in this chapter. But remember that there's two types of sort of energy processes that we commonly come across, and one is a exothermic process. And in an exothermic process, heat and energy is released. And we also have an endothermic process. And in those type of processes, heat and energy is absorbed. So, for example, if we have a bond and we want to break it, we basically have two things that are bonded together. You actually have to put energy in there to actually break that bond. When they do, everybody gains enough energy and they're able to kind of wiggle away from each other. Not exactly how it happens, but we'll pretend. And when you make a bond, it's actually an exothermic process where energy has to be released because you got everybody moving around a lot. So as they release energy, they're going to kind of slow down, and that's going to allow them to kind of come together to make that bond. So again, sort of making and breaking bonds has a lot to do with energy. We have potential energy, which is the energy based on its position. It's kind of stored energy. The classic example, right, is you got the giant boulder up there on the hill. It has a certain amount of potential energy based on its position. And what could happen, obviously, if that boulder goes over the hill there, we can convert some of that potential energy into kinetic energy, for example. And kinetic energy is the energy due to motion. So if this comes over, it's going to kind of convert to kinetic energy. So as I mentioned before, we have the law of conservation of energy, which means energy cannot be created nor destroyed, but it can be transformed from one place to the next. So when somebody loses that energy, as I mentioned earlier, somebody else should gain that energy. So if you take, for example, the boulder, some of that potential energy is going to be converted to kinetic energy. When it does splat on the ground there, hopefully nobody's underneath it, it will also exchange some of that energy to the ground, right? And the ground's going to pick it up, or whoever was underneath the boulder as well. So we do deal with a lot of different types of energy along the way. But again, it is sort of conserved. And a good way to think about it is if somebody, like I mentioned before, either gives away a certain amount of energy, that energy has to end up somewhere and it won't lose anything along the way. Now, as I mentioned before, this study of energy and really the law of conservation of energy is what is referred to as the first law of thermodynamics. And thermodynamics in general, in what we'll be talking about in this class and what you'll talk about it in like 1A, for example, has a lot to do with energy. And again, it's that sort of interconversion of energy and how it plays a role in reactions. As I mentioned earlier, later on in 1B, you'll talk about other aspects of thermodynamics, which deals a lot with, again, whether or not under certain conditions a reaction will just occur or not occur without any type of intervention. Now, one of the important sort of ideas of thermodynamics is state functions. And state functions are properties that basically are determined really by kind of two things: where you start and kind of where you end. And it doesn't really matter how you got there. Things like energy, pressure, volume, temperature, these are state functions. For example, if we look at the hikers here in this mountain, the blue hiker took the more direct route up the hill. Now the sort of red hiker took the more scenic route around the mountain. But in terms of their potential energy at this point, they are the same because they essentially started in the same location and ended in the same location. And that's really all that's important. And sort of a practical application of that, for example, is a lot of times when we see a chemical equation written for a reaction, sometimes we think that it all occurs sort of in one sort of step. And for example, if we have this reaction here, like A plus B goes to E plus F, you may look at it and go, that's probably just going to all occur in one sort of step. And it may not. It may actually occur in several sort of individual reactions to get you there. For example, the first reaction may just be A plus B makes C and D. Then C and D come together to make that E and F that you see. And when you add these together, since these are on opposite sides, they cancel out, and we get our overall reaction, which is actually a sum of two separate steps that occur to get us there. Now, some reactions occur, for example, in 2 steps, 3 steps, 4 steps. Some reactions do occur just straightforward in a kind of a one-step sort of process. Now, in terms of something like energy, it doesn't matter if it occurs, like I said, in all those steps or not. What matters is really where you start and where you end. And that's why when we calculate something like change in energy, change in pressure, change in volume, change in temperature, that's what the delta means, change, we take final minus initial. And that's also why when we calculate something like energy, like we'll do in this sort of chapter, one of the ways that we calculate energy in a very sort of common way that we display energy is to actually take sort of our final state in the reaction minus our initial state in the reaction. Now, since we skipped a few chapters here, and they probably assumed that maybe you read those when they read the book, when we talk about an equation here, these are what are known as reactants. And that's like your starting material. And over here on the right-hand side of the arrow are what are known as products, which is basically your ending material or the stuff that's formed. So a lot of times, like I said, when we would calculate, for example, the energy of a reaction, we would take up all the energy of our products, which is our ending state, and subtract it, for example, from all the energy of our reactants, which is our initial state. And again, those are the kind of two important things. So when you think about a chemical reaction or you see a chemical equation, your products, which are on the right-hand side, you can think of as like your final state, and the reactants, which are on the left-hand side, is what you start with, which is sort of your starting state or your initial state. Any questions on that there? Yeah. So let's talk about some important units of energy here. And by the way, none of these are negative. That's just PowerPoint's dashes. So we'll just scratch those out there. All right. So probably the most common unit of energy that you come across is joules. And joules is a very common unit of energy. It's abbreviated with a J. Another unit that's very common as well, as you can see underneath there, is what's known as kilojoules. So very, very common energy values are given to you in joules and kilojoules. Kilo is 10 to the 3, right? So that's 1,000, as you can see here, joules in a kilojoule. So that is a conversion that we use a lot. 1 joule actually equals 1 kilogram meter squared second squared, which is actually what is referred to as a Newton meter. This relationship here, I would say, not necessary for our class, but as you continue on into 1A and 1B, you will see this sort of relationship that a joule equals that and some formulas that you have to use and stuff like that. So that's a good one to kind of know. I don't know if we'll specifically kind of use it a lot in here, but as you go on to 1A and 1B, that's a relationship that you do see sort of a lot. In addition to joules, a calorie with a lowercase c is also a very common unit of energy. And what goes along with that is a kilocalorie. And there are in 1 kilocalorie, still the kilo conversion, 1,000 calories. Yeah. So again, that is another sort of conversion. Speaking of those two units, you sometimes do need to convert between them. And that is this conversion down here. 1 calorie is equal to 4.184 joules. That is another number, that 4.184 joules. We'll see later on in this chapter. It is basically what is known as the specific heat capacity of liquid water, and definitely a number that you'll need to know. So this kind of pops up a lot. Now, what is a calorie? Calorie is the amount of energy that's required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And for example, we do use, or we do see energy reflected, or the change in energy reflected by the temperature of a substance. And when we see something, for example, gain energy, should the temperature go up or down from where it started from? Yeah, the temperature should go up. So if somebody gains energy, you're going to see that reflection as the temperature will go up. And obviously, vice versa, if somebody loses energy, we will see that basically displayed as the temperature going down. So one way we could see that again is taking, like, for example, ice to liquid water. We will see the temperature change, obviously, as it starts to go into liquid water from where it started from. Now, when we talk about temperature and we also talk about thermal energy is different than temperature. Thermal energy is actually associated with the motion of the atoms or molecules that are present. So the more molecules and atoms that you have present, the more thermal energy you will have. Again, the temperature is different than that. Again, temperature is more of a reflection of what we see in terms of energy either being gained or lost. I have that. So the distinction there, for example, is if you had a cup of coffee at 70 degrees Celsius, it has a higher temperature than the bathtub at 40 degrees Celsius, but the bathtub itself would actually have a lot more thermal energy than the cup of coffee. And that's because obviously if you had a bathtub here with 40 degrees versus just a small cup of coffee at 70 degrees, there is definitely a lot more molecules and atoms in the bathtub, right, of water than you do in your cup of coffee, and it would have a lot more thermal energy. Now, you may be wondering, so why is like the coffee kind of a higher temperature, right? And that has a lot to do with something we'll talk about later on, which is specific heat capacity. And if you just think about it logically, right, that is a much smaller amount of volume of liquid, which is going to take obviously less energy, if you will, to raise the temperature or see a temperature difference than if you try to heat up a bathtub. So if you put like a big giant pot of water up there on the stove and you want to heat it up to make pasta, it's going to take a while, right, for that to sort of start to boil and really heat up the temperature. Now, if you took, like, for example, in the laboratory, a really small beaker and filled it up with some water and started to heat it, it's going to start to heat up a lot faster. It's probably going to get hot a lot quicker. There's a lot less volume. So specific heat capacity deals with the idea of how much energy you have to put in there per gram of substance. So there's a lot of grams, for example, water. So it's going to take a lot more energy to see that temperature difference than it does in a smaller one, like we have here in the cup of coffee. Any questions on that there? All right, so heat is the flow of energy due to a temperature difference. And by the way, heat flows from cold to hot, hot to cold. It flows from heat always flows from hot to cold. So heat flows hot to cold. So the hot object, for example, cools down. The colder object gains the energy and heats up in terms of its temperature. Again, just for example, to illustrate that pretty simply, I did the ice cube example earlier. So when you take out an ice cube from the freezer and just put it on the table, the air around the ice cube is much warmer than the ice cube itself, right? So the flow of heat is going to come from the surrounding air into the ice cube, and now it starts to melt, right? Just like our ice cream melts, right, on a hot day and all that good stuff. Now, opposite of that, let's say you want to actually make ice cubes, right? I don't know if people do that anymore, but if you put it in some water in an ice cube tray and you put it into the freezer, at that point, once you put that water in that ice cube tray into the freezer, the water is more like room temperature, right? The freezer air is obviously a lot colder. So what's going to happen to the water in that tray is all the heat's going to leave the water in the tray and go out into the surrounding air in the freezer. The result of that is the water in the tray is going to lose energy, and now you have ice cubes, right? So you got ice cubes that are made in that case. So we always have a flow of heat going from that sort of warm object or hotter object to cooler object. As we talked about, there are two types of main processes that we deal with. And again, exothermic process is anyone where heat and energy is given off. Endothermic processes are when we absorb energy. Probably the two ways that we will display sort of energy in chemistry are these two ways. One is what is referred to as the delta H, which we'll talk more about in just a second. And that is what is known as the change in enthalpy. That is a fancy way of saying typically how much heat or energy is associated with a reaction. So either absorbed or released. Now, when we have an exothermic process, as we will talk about, the delta H value for that is always a negative value. So you always end up a negative value for that. While the delta H value for an endothermic process will be a positive value. Another way that we sort of also signify sort of heat and energy in chemistry that we'll see in this chapter is Q. And Q is basically heat, or if you want to think about it, energy as well. And Q as well, when you calculate something that is a exothermic process, will be a negative number, and Q will end up being a positive number. So in essence, when you're dealing with energy or you see energy sort of values in chemistry, typically if you have a negative energy value, that is basically indicating to you that that process is an exothermic process. There's some heat and energy is being released in that situation. If you have a positive value for energy, essentially that means that's an endothermic process. Heat and energy is going to be gained. We saw earlier as well in the previous slide, delta E, which is also the change in energy. Works the same way for that. If you have kind of a negative delta E, you got it released. And if you have a positive sort of delta E, you have an endothermic process. So that's why, for example, as we get into some calculations in this chapter, and in general, when you do calculations involving energy in chemistry, it's important to actually keep the negative sign that you get if you actually do a calculation and you end up with a negative sign, because it does indicate, what is happening in terms of the energy is being released. Or if you end up with a positive, obviously that's important as well. Sometimes people are taught these type of calculations, they'll don't worry about the negative or positive, but it actually is a kind of an important aspect of it, as it will kind of tell you what's going on in that process. Any questions on that there? All right. So when we have a chemical reaction and when we go from our reactants to our products in a chemical reaction, and again, our sort of starting and final, if you will, sort of state, the only thing that happens in a chemical reaction is all we do is basically break bonds and we make bonds. So that is essentially all that takes place in a chemical reaction. And that all involves electrons. And so we never ever change any elements and in a chemical reaction because it only involves electrons. So we have that conservation of the elements because of that. So when we break bonds, we're doing that to our reactants. And what that does is free up everybody to come back together on the product side as perhaps new things. These are what are referred to here on this page as energy diagrams. And when we look at energy diagrams, there's a few important spots to it. And we have here, maybe I'll redraw it over here. So just to kind of redraw similar type of graph there. So that is energy. This is the reaction that's progressing. And I think the first one we had there, yeah, was that. So we got something like this. Now, this is where our reactants are in terms of energy. This is our products. And the first sort of thing that happens, as I mentioned, is since we are only breaking bonds and has to make new bonds, what happens is as reactants start to collide with each other, they actually need two things to sort of occur for a reaction to take place. First, they actually do need to kind of come in contact with each other, hit each other, if you will. They actually do need to actually hit each other in the right location for a reaction to take place. So just because two reactant molecules, for example, come together, it doesn't necessarily mean that they will actually form any products. They got to hit each other in the right location. And they also have to hit each other with the right amount of energy to kind of kick off the reaction. So what happens is as they collide and they do have those two things, the right location, the right amount of energy, what's going to happen is these reactants are going to start to break bonds. And at the same time, they're going to actually start making as well. So they're going to break and start making bonds at the same time as they kind of come up this hill of energy until they get to the very top here. And at the very top here, this is what is sometimes referred to as the transition state. And the very top here is really the highest point in terms of energy, right? And one of the things in terms of energy and chemistry that you should understand is things in high energy is not really favorable. That's really an unstable situation. Things do not really want to be in high energy. Things like us want to be in low energy, right? On the couch, not doing too much, right, all day. So the same thing happens here in chemistry. So a lot of what happens in chemical reactions and when things react with each other, bonds breaking, bonds making, when bond forms to make a certain compound, a lot of those things are all ultimately done to lower the energy of everybody to a more stable sort of situation. So what happens at the transition state here is it will sort of come down really quickly a lot of times to the other side because it's very unstable. And when we look at the energy of our reactants here versus the energy of our products, what we see is our reactants are higher in energy than our products, which means the only way our reactants can get down to our products in terms of energy is energy has to be released here in this reaction. And that will allow our reactants to get down to our products. And when energy is released, this is a exothermic diagram of what is going on. And you always know it's an exothermic diagram because the reactants are higher in energy than the products. And that is always a situation when you see a diagram like this that would indicate a exothermic reaction basically taking place. Now, that hill that the reactants need to climb to get to the other side from here to here also has a special name. This is what is known as the activation energy. It is sometimes abbreviated E of A, and that is the minimum amount of energy needed for a reaction to occur. Now, it is sort of the energy barrier, if you will, for the reactants to get to the other side. It affects the rate of a reaction, how fast it will actually take place. Again, if you have a really big activation energy, then it's going to take a long time for things to maybe get up and over to the other side. You may not have actually a lot of guys in the reactant area that could actually make it up and over that hill, and it may be a much slower reaction. When we get to the very top of this hill, as we talked about a second ago, that it is kind of the highest energy state, what you have is what is sometimes referred to as a transition state complex. And sometimes they'll have like a weird, like little symbol sort of above it or something like this above it. And the transition state complex is something that has partially made bonds and partially broken bonds. And it's in a really transitional period because it's sort of losing those original bonds and starting to make those new bonds. And again, that makes it very, very unstable because it got partially made and broken bonds, which, as I said, very commonly, very hard to isolate, and it will kind of drop down very quickly to our product side. Now, when we talk about this type of reaction, which is an exothermic diagram, when we look at something like delta H, as we will talk about, which again is a way in which we can represent energy in a reaction, one of the ways we calculate the delta H of a reaction is to take the delta H of our products minus the delta H of our reactants. Again, our final minus our initial sort of state. So when we look at that here, that is the difference between the energy of these two spots. That would be our delta H in this case. And if we just look at sort of the location of our reactants versus our products is a much smaller energy value because it's way over here. So you're going to take a small number basically, and you're going to subtract it from our reactants, which is a much higher energy value, from a much larger number. This is going to why it yields you a negative value when you calculate the delta H for an exothermic reaction, because the energy of all your products are going to be less than all the energy of your reactants that you started with. That excess amount of energy gets shot out from the atom and released from the atom in this exothermic sort of process. Any questions on that one there? Now, endothermic looks similar, but it is a little bit different when we look at an endothermic sort of diagram. So we have energy, we have our reaction that's proceeding in this direction. So in an endothermic diagram, we got something like this, where we have, say, our reactants, our products here. Once again, in this situation, our reactants are actually lower in energy than our products. So again, the only way for our reactants to get up there to our products is energy needs to be absorbed in this case to allow our reactants to get up there in terms of the energy where it needs to be for our products. We also have the same sort of activation energy, which is from our reactants to the top of that hill. That is our activation energy. You could also see that in comparison to our exothermic reaction. Typically, an endothermic reaction has a larger activation energy hill, which also makes sense. This overall energy needs to be put in there to help everybody get up and over that hill. So it has a bigger hill to climb for our reactants. Same thing's happening. We're starting to break bonds here. We're starting to make bonds. We'll get to our transition state up here. And again, it will kind of come down to our products. Now, just like before, what's going to happen when we look at this is the energy difference between our reactants and our products, once again, is going to be our delta H for this reaction. So that's going to be our delta H. And again, if we think about what's happening here when we calculate delta H of our products minus the delta H of our reactants, our products in this case are much higher in energy. So you're going to actually take a large number minus our reactants, which are lower in energy, and we will have a smaller value, and that is what's going to turn your delta H into a positive number. So again, that is a very common way, as I mentioned in chemistry, that energy is sort of displayed for a reaction is by basically the delta H value. And really the nice thing in terms of the delta H value is if you want to determine is it an exothermic reaction or an endothermic reaction, it really doesn't matter the actual number. It's all about really the sign. Is it positive or is it negative? And that's really all you have to kind of look at to determine whether or not this is going to be an exothermic or endothermic reaction. Now, one of the ways that we can, for example, speed up a chemical reaction, a lot of times to speed up a chemical reaction, we add what is known as a catalyst. And a catalyst is not a reactant. It is not a product. And it also does not get used up in the reaction. It is really there for one purpose, which is it is there basically to make that reaction occur a lot faster in most cases. There are catalysts that typically will slow down a chemical reaction, but I would say that probably 99 times out of 100, if you're asked about a catalyst or somebody's talking about a catalyst, in most cases, people are talking about a catalyst in the effort of speeding up a chemical reaction. So, how does a catalyst ultimately speed up a chemical reaction? Speaking of catalysts and chemical equations, you oftentimes will see the catalyst written on top of the arrow in the chemical equation. And it could be something like a metal, like platinum. It could be something like an acid that's sometimes written as H plus, which is basically like an acid being used as a catalyst. So, for example, just a simple sort of example to illustrate sort of what a catalyst is able to do. A catalyst essentially is able to find a more efficient pathway, if you want to think about it, for that reaction to take place. That if the catalyst was not present, it would take much longer for everything to happen. So, for example, if we had some gas molecules in a reaction, and basically for the reaction to take place, they have to go find each other. Now, if they're just flying around by themselves, sort of in the container, it conceivably could take a long time for them to kind of come in contact with each other, make the collision with the right amount of energy in the right location and stuff like that, which could affect how fast that reaction will take place. Now, let's just say we have these same sort of gas molecules floating around, but we add in some type of metal, for example, that's a catalyst. Now, this metal may have the ability to attract, for example, these gas molecules towards it. So instead of those gas molecules just flying around, they're going, oh, cool, metal. They're going to kind of come towards it. When they come towards it, what that's going to allow to happen is those guys to get in contact with each other a lot quicker. And the end result of that is that should also kick off the reaction and have the reaction occur a lot faster as they're now quite close to one another. It shouldn't take very long for these guys to start interacting, start breaking bonds, start making bonds. And in some cases, the metal could actually help out in the process of sort of breaking some bonds and making some of those new bonds. So a catalyst finds a really an alternative pathway, a more efficient pathway for that reaction to occur. Ultimately, what does it do in terms of like our energy diagram? What it does in terms of like our energy diagram is it's able to, a catalyst, basically lower the activation energy. So remember that that activation energy is the hill that the reactants has to climb to get to the other side. So if they have to climb a really big hill in terms of energy to get to the other side, the reaction is going to occur probably a lot slower, right? Just like if we all had to walk a giant hill to get to the other side, maybe not all of us go up that hill, not going to want to walk up that hill, right, to get to the other side. But if we only had to walk up like a speed bump, like in the parking lot, right, most of us can go, not a big deal, right? We could get up and over. We can get a lot more people get to the other side a lot quicker. So instead of, for example, in this reaction, the reactants having to climb this hill basically to get to the other side, by finding this alternative pathway, what ultimately the catalyst is doing is it's lowering the hill to get to the other side. So instead of having to go up the green hill to get to the other side, all they have to basically get up to the other side is that kind of purplish hill there. And what that's going to allow is more reactant molecules will then have a lot more energy or enough energy to make it up and over that smaller hill to get to the other side. Again, the result of that is you can get a lot more products being formed, and the rate of that reaction is going to occur a lot faster. Any questions on any of that there? All right, so here again, it's just another sort of version of an energy diagram. This is our reactants, and I know those are our reactants because they are on the non-pointy side of the arrow. The arrow always points to our products. And once again, what we see here is an energy difference from where our reactants start to our products. the net result of that is we're going to have to give off that energy to our surroundings, as opposed to over here where we have our reactants and our products. And again, in this case, our reactants are lower in energy than our products, so energy is going to have to be put in there to get up to those products in terms of where they are located. So as we've been talking about, exothermic reactions and endothermic reactions are important types of processes. They basically are the two major processes that occur as a reaction takes place. And when we think about energy and an exothermic process or an endothermic process, we also think as energy as being either, for example, a reactant or a product. And it's not correct in all aspects, but a lot of times we do think of it that way. So if we have a exothermic process, you usually will think about heat, which this is a energy value here, 213 kilocalories, as being on as a product in the side, like it is being given off basically. And sometimes you may even see it written into the equation, like we see here, an actual value for heat or energy, or simply they just may say on the other side like plus heat. And again, that would indicate, because it's written on the right-hand side of the arrow, heat and energy is a product, and this is a exothermic process occurring. As opposed to an endothermic process, we think of heat and energy more as a reactant. And again, what that means is like that energy is being absorbed by the reactants to get to the other side to our products. And again, it could also just be written generically like that as heat. So again, if heat is actually written in the equation as either a actual value or just a word heat, the side that you put it on is important, because again, if you put it on the product side, you're indicating that this is going to be releasing that energy as an exothermic process. If you put it on the reactant side, it is basically going to be absorbing it. Now, I would say probably you'll never see it written like that in most cases. Most cases, the way that you will see whether or not a reaction is exothermic or endothermic in chemistry is this. If it is a exothermic reaction, you will just simply have the reaction written, and at the end, you'll have a delta H value that's negative, and they'll give you like the delta H value for the reaction. Or if it's endothermic, once again, it's usually not written into the equation, and you'll have that delta H value that's positive. So probably I would say 9 times out of 10, or even more than that, that is how, when you see an equation, for example, and maybe a delta H value or an energy value, that is how it's usually given to you to indicate to you if it's exothermic or endothermic. They just simply give you a number at the end, like, hey, minus 150 kilojoules, or positive, 225 kilojoules. They obviously want to write the positive in most cases in this case. Any questions on that there? So as we were talking about, again, that transfer of heat and energy from hot to cold, we'll see basically the energy coming in this direction here. And eventually what will happen is, as we were talking about, that cold water will start to warm up. As the hot water loses that energy, it's going to start to cool down. And if they're kind of in an insulated container like in here, they'll meet somewhere between their differences there, right? 90 and 10 is 100, divided by 2 is 50, so they'll meet somewhere in the middle. They will come to what's sometimes referred to as equilibrium, right? Everything will basically be the same temperature in that situation. So enthalpy, as I mentioned, and we sort of been touching upon, is really in chemistry the way that we oftentimes will display the energy associated with a reaction. The change in enthalpy, again, is the products minus the reactants. And when we calculate it from an equation, the delta H of the reaction, we typically need to go usually to a table like in the book. And the table will have these, what is sometimes referred to as a delta H of F, is sometimes referred to as that. That is a delta H of formation, is what the F stands for. And you'll find listed in there all elements, compounds, molecules, whatever it may be. Everything will be listed in there with a value. Now, what you'll see is, in general, if you have a delta H value for anything that is in its natural state, anything that's an element, anything that is uncombined with any other element, they typically will have values of 0. and everybody else will have other values. The other important thing is when you go to this table, for example, you do want to make sure that you find what you're looking for, but you want to make sure that it is in the correct state. And if it's not in the correct state, you want to make sure you find the one that is. I would say most commonly people go to like a table like that and they find like the first water they see, and it may not be the correct water that they need because maybe they need ice, which is the solid state of water. Maybe they do need liquid water, or maybe they need steam, which is the gas phase. So it's really important to make sure you look it up in the right sort of way. They are typically given in units of kilojoules per mole, and mole is a unit that we'll talk a lot about this semester. But one of the ways when we look at an equation, say we had 2a plus 4b goes to c plus 3d here. If we wanted to calculate the delta H for this made up reaction, we would take the delta H of our products minus the delta H of our reactants. So I'll just make a fake table here of A, B, C, and D. And we'll go negative 50 kilojoules, 125 kilojoules, negative 111 kilojoules, and why not? Let's do a 60 kilojoules and see how bad I did there. So these would be, for example, the values that you would find in the table. You would want to go to this table here. Obviously, it would be provided for you if you needed it. You would find everybody that you need. Now, one important thing when we do our products minus our reactants is in an equation, there are coefficients. And coefficients are these numbers that come in front of the actual formulas in a chemical equation. Now, if there is no number in front, it is assumed to be 1, right? So, for example, this guy is assumed basically to be 1. We typically don't write the 1 in, but it is assumed to be 1. Those are what are considered the moles of each of these things. So when you calculate this, you do have to multiply the coefficient times the number that you find in the table. So if we were going to calculate this, our delta H of our reaction would be starting on our product side. We have 1 times the value that we'd find for C. So we would take 1, and again, you don't necessarily have to do the 1 here, minus 111 kilojoules per mole. We're then going to add it to 3, which is the coefficient here, times the value for D in our table here. We take 3 times 60 kilojoules per mole. And pretty much this is all of our products, right? That's everything we got going on for our product side. We're then going to subtract it and do basically the same thing for our reactants. So on our reactant side, we have 2 of A. So we're going to take 2 times the value of A that we have in the table. We're then going to add it to our other reactant, which is B, and there's 4 of them. So 4 times the value of B in the table. And basically on the bottom here is everything from our reactants. This again is what we were talking about, sort of state function, final state products minus initial state reactants, right? And if we do all that, let's see how bad I did here. So we ended up with minus 111 plus 3 times 60. So that's going to give me a 69 minus 2 times negative 50 plus 4 times 125. They give me approximately 400, I think, here. So basically, we got 69 minus 400. Going to give you overall here negative 331 kilojoules in this case. And that would be the delta H for this reaction that I just made up. That would mean that my reaction is endothermic or exothermic. My reaction is exothermic, and all I need to know about that is I have a negative value here for my delta H, and that's really what tells me it's exothermic. So overall, this reaction is going to release energy, right, as it's doing it to the surroundings in this case. Any questions on that there? All right, we're laid up there for now.